All right, we're back. We are on page 1 of notes 19 of Calc AB. We're going to talk about motion and antiderivatives. So a long time ago, we talked about motion and derivatives, and that's when we learned, position, velocity, acceleration, moving to the left, moving to the right, moving up, moving down, positive acceleration, negative acceleration. We talked about speed. All those things are still relevant. Now we're going to talk about kind of adding in the concept of antiderivatives, see what they give us, and then we'll have like a pretty complete understanding of things that move along a straight line, so either a horizontal axis or a vertical axis. Then if you're in Calc BC or when you get to Calc 2, you'll look at parametric equations and you can move like all over the place. But let's see what we can do now. So a particle moves along the y-axis, so it's moving up and down on the y-axis. It starts at y equals 3 when t equals 0. We have a graph of the particle's velocity, so that's important. This is velocity. So graph of velocity as a function of t. All right, so I don't always label it, but I probably should. Like this is v of t, this is t. There are no units given, which is actually a pretty common thing in AP calculus, and it's kind of annoying because then you'll be asked like, find the velocity and the acceleration. You're like, what are the units on these things? But they're just not given. So sometimes they are though, so watch out for that. All right. Determine the particle's speed at t equals 6. Is the speed increasing, decreasing, or constant? Full review, right? So speed is the absolute value of velocity, which I don't think are actually going to need here. Speed will be increasing when velocity and acceleration have the same sign. It will be decreasing, it being speed, will be decreasing when velocity and acceleration have opposite signs. Speed will be constant when acceleration is 0 because you're not changing your velocity. So I need to figure out the velocity and the acceleration. So v of 6. So v of 6 is, this is a graph of velocity. So v of 6 is definitely down there. It's -3. Should use pointer for that right there. So the velocity is -3. The acceleration, so a of t in general is v prime of t. So a of 6 is going to be equal to 0. Because v of t is constant, right? So it has no rate of change. The rate of change of v of t is 0 on 4 to 8. Okay, so v of t is negative. Well, it doesn't even matter. V of t, the velocity is constant, right? So your speed is going to be constant. So I'm going to say, since a of t equals 0 at t equals 6, speed is constant. So it's constant speed. At what time does the particle reach the origin? All right, so let's think about what's happening. We have a thing that's going to be moving. Like, so here's our y-axis, let's say. All right, so that's your y-axis. At t equals 0, it's going to be located at 3. So let's say this is 3. And we're here at t equals 0. Well, the velocity is positive until we get to 3. So from 0 to 3, we're going to be moving up. Furthermore, we actually, because we understand how definite integrals work, we're at t equals 3. No, we're not. We're at y equals 3 at t equals 0. And then from 0 to 3, we're going to add, so this would be a square that's 4 by 3. So that'd be 12. So half of that is 6. So when t is equal to 3, we're going to be at 3 plus 6, right? So this is 6. So let's say that this is 9. You're going to get there at t equals 3. So y rate 6. And the reason for that is that you started at 3, you gained 6. So by the time t equals 3, you're at 9. When you get to t equals 9, you're going to turn around because the velocity changes sign. Now, what are you going to do? You're going to go, this is 3, what am I trying to answer here? At what time does this particle reach the origin? Okay, so to get to the origin, I now need to go 9 units, right? I need to get down 9 units. So I need to accumulate 9 negative units on this graph. So let's see if we can work out when that's going to happen. So this is going to be, this is -1.5. -3, this region here would give me -6. So I need another -1.5. Fortunately, the geometry of this is like not terrible. Like if I just cut this in half, right? Because the full block would be -3, so this will be another -1.5. So I think at t equals 6.5, we're going to get there. So what happened? We started at 3 at t equals 0. From 0 to 3, we pick up 6. So now at t equals 3, we're at 9. Now to get to the origin, which is y equals 0, I got to go down 9. So I have to lose 9. So by t equals 4, I've lost 1.5, which would mean since I started at 9 and I lost 1.5, I'm at 7.5. By the time I get to t equals 6, I've lost another 6. So now I'm at positive 1.5 at t equals 6. Then at t equals 6.5, I get to the origin. So t equals 6.5, I think, is one time. Then we need to see if there's more. So at the origin, at t equals 6.5, because 3 plus the integral from 0 to 6.5 of v of t dt is equal to 0. Now, let's see if there's another time. I think there's not going to be another time. And the reason I think there's not going to be another time is, let's see, so you're going to lose 1.5, 3, so 4.5. And then this is 2 by 3 is 6 and half of that. So that's another -3. So that's -7.5. You will be, because you were at 0, you're at y equals 0 at 6.5, and then you lose 7.5. You're at -7.5 by t equals 10. And then you just don't accumulate enough more to get back up to 0. So there is no other time at which you're going to be at the origin. So that's the way you want to start thinking about it. Think about it as like, you started at a place, you moved, right? So we started at y equals 3 when t equals 0. But then we knew where we were at t equals 3. At t equals 3, we're at 9. So now base your arguments on that. All right, so when will I be at 0? So I'm at y equals 9 here. I lose 9 here. So now I'm at 0. I'm going to keep losing, right? So I'm at 0. I'm at y equals 0 here. And then I lose 3, another 3, and then 1.5. So 7.5. I'm down at -7.5 here. And then I gain 2. -5.5 is not 0. So you never get back to the origin. So that is the only time. And this would be my justification. And you don't have to like necessarily justify that there are no other times, so I'm not going to. All right, find the absolute lowest and absolute highest points reached by the particle. This is absolute max min. Absolute max min, you know right away you're using candidate's test, which is really like the best test because it's so straightforward, right? So all that we need is for the function to be continuous. But what function? Well, the function that we need to be continuous is actually the position function, which I'm going to call y of t, and I'm going to define it. So pretty confident that these notes come after the accumulation functions notes. I should probably have checked that before, but I'm going to just define a function and say y of t is where we start, which is at y equals 3, plus the integral from 0 to t of v of, I need a dummy variable. I'm going to use u, I guess. Du. Could have used x. That would have been totally fine. Just can't really use t there because it should be a dummy variable. This is my function, and I'm going to say this is continuous. Therefore, so why do I know that it's continuous? Well, if I have to justify that, I would say it's continuous because y prime is v of t. V of t exists for all t between 0 and t. And if the derivative exists, that means the function must be continuous at that point. So it's definitely continuous. Usually you don't have to prove why it's continuous. You can just assert that it's continuous. So I'm going to say, therefore, by candidate's test, absolute max min an endpoint or critical point. So for the critical point, y prime of t is, this second fundamental theorem is v of, you take the upper bound, you plug it in, then you multiply by the derivative of the upper bound, but it's just v of t. So this is for a critical point. Y prime, this doesn't really look like a y prime. y prime equals v of t equals 0. So that happens at, I feel like we've talked about those points. T equals 3 for sure, t equals 10, 3 and 10. Okay, so now we just make our table. We got t, we got y of t. So at 0, which we know is 3, at 3, at 10, and at 12. Okay, so we've talked about, and actually we put it on the put it on here. At t equals 3, we know that we're at 9 because you started at 3, and then you accumulate 6. 3 plus 6 is 9, so that's definitely 9. At 10, all right, so we're at 9. And then what is the total region here? I'm considering erasing some stuff and just kind of like doing it again. I don't know, maybe I won't. So this is negative 1.5, and then this whole thing is 4 by 3. That's negative 12, and then this is, it would be 2 by 3, but then it's half of it, negative 3. Negative 15, negative 16.5. So we lose 16.5, but we were at 9. So what is 9 minus 6? What did I say? Negative 16.5. What is 16.5 minus 9? 7.5. Also, I think I worked that out before. Negative 7.5. I feel like that is correct. I feel like I worked that out. So like this one was given. This is 3 plus the integral from 0 to 3 of v of t dt. The way that I really calculated this is I did 9 plus the integral from 3 to 10 of v of t dt. So like the function you say you're using and the way you actually do it aren't necessarily the same. You want to say the function so that like you can get out your continuous and like anything you need to do there, but then like get the values however you choose to get them. So the next thing we know is that from negative 7.5, we only gain 2 because this region is 2. It's half of 4. So we're going to gain that, and then we'll state our answer. So we gain 2, so we're at negative 5.5, and really what we did was negative 7.5 plus the integral from 10 to 12 of v of t dt. Okay, so I'm going to say, therefore, the absolute max is 9, and that occurs at t equals 3. The absolute min is negative 7.5, and that occurs at t equals 10. There we go. Okay, candidates test. It's gonna come back. It's a big deal. Is it the biggest deal? I guess like it's a tie probably between accumulation functions and candidates tests for like what you end up doing with this stuff. I don't know. All right, so that's first page. I'm gonna cut this here. I will be back in the next one to do the next page. So see you there.